Coach Wade is going first.
Pick a number between 10 and 20.
It's 20.
20, let's
Yes!
go!
All right, so Coach Wade's got to do 20 spins and then run up and hit the ball.
All right. Hold on. Get ready. Okay, go.
1, 2. $19, $20, go, 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 go! Oh my gosh!
I surrender.
You win. Well, let's just call it a day.
Bobby Yamamoto.
Alright, so this lecture we're looking at section 12.4, which is the inscribed angles and everything associated with inscribed angles. So what is an inscribed angle? An inscribed angle is an angle with a vertex on the circle whose sides are chords of the circle. So an inscribed angle is where you take, just a second, where you take a circle and you connect. So here's a chord, here's another chord, but the vertex, this guy right here, has to be on the circle, like actually on the circle, and the sides of the, notice how it creates an angle here, the sides of that angle are chords. So that's what an inscribed angle is. Another example, you could take a circle like this. That would be an inscribed angle there. So you see you get a wide variety of types of angles, what they look like, but that's the definition of an inscribed angle. Now an intercepted arc is a portion of a circle contained between two endpoints of an inscribed angle. So the inscribed angle in this case, the inscribed arc, I already talked about the inscribed angle, the inscribed arc would be this arc right there. Notice it's contained between the two endpoints of the circle, and that would be my inscribed arc. Now last definition, we're going to say that a chord or arc subtends an angle if its endpoints lie on the sides of the angle. So basically just think almost like, just like to say reaching out or tending to or converging to, going to, that's what it means to subtend, just going to in a sense. It's kind of a weird definition. Now our first theorem is the inscribed angle theorem, and this theorem states that the actual measurement of the inscribed angle is half the measure of the intercepted arc. So the inscribed angle is 1/2 the arc measurement. So let's relate this back to what we've talked about before. If I'm looking at, here's the arc we're looking at right here. Let's say that's arc AB. Let's say that the measure of arc AB is 40 degrees. Well, what would be the central angle here? Remember, that is my central angle. What's the measurement of the central angle? Hopefully remember that it's the same. It would also be 40 degrees. So the relationship between the central angle and the inscribed arc is that they're equal. Well, the inscribed angle, this angle down here, this is going to be half the arc measurement. So it's going to be 20 degrees. So this is I've seen a lot of mistakes made here, but don't overcomplicate this. If I take a circle, and here is, say, the arc, the inscribed arc created by these points. Let's just say that this is 50 degrees. The central angle, also 50 degrees. If I take a circle, let's say that this is 30 degrees. The inscribed angle here is half of 30, which will be 15. So if it connects to the center, it's the same. If it goes from one side to the other side, it's half. It's that simple. Conversely, you can go the opposite direction if you know that this is 15. Then you can double it to get to the arc measurement. And that's the converse of this theorem. Now, there's really three cases of your inscribed angle. Case one is that one chord goes through the center, making it the diameter. The center of the circle is in the middle of the arc, of the angle. And last is that the center is outside of the inscribed angle. So that's three separate cases that you might come across. Alright, so our next corollary, remember corollary is the next logical step to our theorem, theorem 12.4.1. So our next logical step to this corollary 12.4.2 states that if inscribed angles of a circle intercept the same arc or are subtended by the same chord or arc, then the angles are congruent. So what does this mean? Let's look at a simple example first. Let's say I had that circle here, and I have my first inscribed angle. So it's reaching up and grabbing onto that arc right there. Now if we were in class, I would draw the following picture. Let's say here is a football player. Here are his arms reaching up, and he's grabbing onto this football here. So that football player is reaching up and grabbing onto that football, and that football represents the arc. So he's grabbing onto that arc. Now, let's take another football player. Let's say he's reaching up and grabbing onto the same football, trying to catch the same football. So here's his arms. He's reaching up trying to grab the same football as the first player. Well, the heads represent the angle measurements, which means that if they're both reaching up and grabbing onto the same football, the same arc, then the angles here, they're both congruent / equal. That's a kind of silly, stupid example, but that's the idea. They both reach up to the same arc, the same football, which means that the angle measurements are the same. So all you got to do is, if you ever see a circle like this, well, your conclusion, since they both subtend or reach up to the same arc, these two angles are equal / congruent. It's that simple. But let's make it more complicated. Let's say that I had this example. Well, to do this, let's just start looking at all the different arcs that we see. Let's start with arc AB right there. Now, which angles do I see reaching up to that arc? Well, I have this angle here, angle ACB. I have this angle here, ADB. And then I also have this angle right there, AEB. So all three of those angles reach up to the same arc, which means they're all congruent / equal. So that's my first arc. Let's kind of work my way around and see if I see any other arcs. Do I see any angle subtending or reaching up to arc AC. Well, that doesn't work. Might think this one, no, because it's missing that part. So I don't see anything reaching up to that arc. Let's look at arc CD. Looking at arc CD, I have CBD, and I also have CAD. So I have two arcs reaching up to that same arc CD. So I could say angle, or angles, not arcs. I have two angles reaching up to that arc. Angle CAD is congruent to angle CBD. And I hope I didn't say arcs for these. They're angles. Sorry if I made that mistake. So that's the angles with this arc CD. Let's keep working around. I got DE. Which angles do I see reaching up to that arc? Well, I have DAE. I have DBE. So I get angle DAE is congruent to angle DBE. And if I can keep continuing, I have this arc here, nothing subtends to that. So that one doesn't work. So am I done? Well, we have actually one more, this big arc here, C to E. Which angles reach up to C to E? We have CAE, and I have CBE. So that's my last two pairs, and I don't think I missed any. Pretty sure I got them all. But hopefully you see how it might get a little bit complicated if you start adding a lot more angles. But do like I did, just kind of work your way around the circle, looking at all the different arcs, and hopefully you can catch them all. Well, how do I use this to actually solve different questions? Well, our first example here asks us to find the measure of each. Let's start with the measure of angle LMP. LMP. So what would that angle measurement be? Well, if the arc here is 36 degrees, to get to the inscribed angle, I just take 36, divide by 2, and the measure of angle NMP is equal to 18 degrees. Now let's look at the arc, measure of arc MN. Well, if the inscribed angle is 48 degrees, to find the arc MN, I take 48, multiply by 2, and I'll get the measure of arc MN is going to be equal to 48 times 2, which is 96 degrees. So it's that simple. Example 2, let's solve for the measure of FJH. So FJH, this angle right there. Well, notice that these two arcs reach up to these arcs. These two angles, subtender, reach up to the same arc right there. So since they go to the same arc, reach up and grab the same football, those angle measurements must be equal. So I can write a little equation. 5z is equal to 4z plus 9. Solving gives me z is equal to 9. But as for the arc, the angle measurement, so I can plug it back into either of these, and I get the measure of angle FJH is equal to 45 degrees. Our next theorem states that an inscribed angle subtends a semicircle if and only if the angle is a right angle. So the if and only if, hopefully you guys remember that as our biconditional. It works both ways. So really what's going on is that you could say our first direction, if an inscribed angle subtends a semicircle, then the angle is a right angle. So if you take a circle, and here is the semicircle. If you take an angle, an inscribed angle, and if it reaches up and it ends on the semicircle, my conclusion is that the inscribed angle is a right angle, or 90 degrees. Conversely, working the opposite direction, we're going to say that if we have a right angle, as an inscribed angle, then it subtends a semicircle. So the opposite direction is that if you have an inscribed angle, and I know that it's 90 degrees, it's a right angle, my conclusion is that it falls on the semicircle. So that's what our next theorem is. Now, how to actually use this? Well, example 3, let's solve for x. Well, notice that this right here is the diameter. It falls in the semicircle. It is a semicircle. So since the inscribed angle falls in the diameter, which is a semicircle, I know that this angle has to be 90 degrees. So it's super easy. I just take 5x plus 8, set it equal to 90 degrees, or 90, and then I solve. So I get 5x is equal to 82. I subtract 8 from both sides, and then x is equal to 16.4. 82 divided by 5, 16.4. So that's how you solve for that question. You could also use the converse as well to solve for the unknown. Alright, our last theorem for today. If a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. And what does supplementary mean? Remember, they add to 180 degrees. So if you take a quadrilateral and it's inscribed in the circle, which means that the vertices, if I could do this, of the quadrilateral fall on the circle. So all 4 parts where the quadrilateral comes together, they have to be on the circle. You couldn't have something like this. That would not be inscribed because this one does not fall in the circle. That if that happens, then your opposite or across angles, they are supplementary, or they add up to 180 degrees. So angle A and angle C are supplementary, angle B and angle D are also supplementary. So to solve this, a question that you might come across, this example here, let's solve for x and y. Well, what are my across or opposite angles? Well, I have angle W and angle Y. And I have angle X and angle Z. Those are my opposite angles. So what that means is that the opposite angles are supplementary. So let's solve for our first one. I get 2x plus 4 plus x minus 4 equals 180. I add them up, set them equal to 180 degrees. 4's cancel out. 3x equals 180, which means x is equal to 60. Now, I'm not done because it asks to solve for the actual angle measurements. So let's go and plug those back in really quick and solve for, let's say y. I don't know why I said y earlier. Let's solve for each of the angle measurements. And the measure of angle W, 120 plus 4 gives me 124 degrees. Angle x is just x degrees, so that would be 60 degrees. Angle y, 60 minus 4 gives me 56 degrees. And then angle z, 2 times 60 is just 120 degrees. Now, at the beginning I thought there was a y, so slight misreading there. But I could have also set these two equal to each other. Or not equal to each other. I could have taken those two and set them equal to, add them up, set them equal to 180. So I could have done 2x plus x is equal to 180, which gives me 3x equals 180, x equals 60. Now if that were, let's say that were a y or something, I could also solve for a different variable in that aspect. But they're supplementary, so you add them up, set them equal to 180, and then solve for the unknowns. And that is it. So if you guys have any questions about anything, shoot me an email. We can do a Google Hangouts or anything else. But yeah, so remember your quiz this week is on Thursday at 10 a.m. I'll email you if you're in the second group, or email me if you need to be in the second group. But shoot me an email if you have any other questions. Have a good day.